Okay, welcome back. We're now going to finish this tour of shallow marine deposits by looking at tide-dominated shorelines and parasequences. So back to our triangular diagram, and we're thinking about environments in this closest to this tidal corner of a triangle. So estuaries and tidal flats, essentially. We'll focus principally on tidal flats. Tidal flats occur in both transgressive and regressive settings. Estuaries tend to occur in transgressive settings. They're commonly drowned river valleys. We'll talk about those a bit more in a later session. So what are tides? Well, here we've got data from a tide gauge. The vertical axis is water elevation measured at this particular location, and on the horizontal axis we've got time in days. So this represents 30 days, 31 days, so 1 month. What we can see in here is that the water elevation goes up, down, up, down, up, down. And we can see there are several different sort of cyclicities to that variation. One is if we go from high to low to high tide, that represents basically a 12-hour period. Okay, that's a 12-hour or semi-diurnal. That means half a day period. We can also see if we go between successive high tides, we have one which is slightly higher, one which is lower, one which is slightly higher. So these represent a 24-hour period. So a daily cycle or a diurnal cycle. And we also have longer term periods. So if we look at these maxima in the high tide and equally the minima, the low tide positions, we can see there are periods when we have a large distance, a large range between the high and low tide. Those are the spring tides. And then we have periods or times when there's a low separation, a low range between the high and low tide. Those are the neap tides. And if we go from the spring tide to the neap tide to the spring tide, this represents a period of about 2 weeks, about 14 days. So this is a neap spring cycle. So, we make these observations that there's these periodic or regularly repeating fluctuations in the water elevation. These are the tides, and we can see they occur over several different durations, several periodicities. So that's what tides are. How do they form? Well, what we're seeing here is a schematic of the Earth on the left, the Moon on the right. And we're imagining here that the Earth is a perfect sphere and that we have a layer of water around the Earth, which is basically of uniform depth. And there are two sort of competing forces that act on that water around our idealized Earth. So one is gravity, and gravity are basically these thin arrows in here. Gravity pulls water on the Earth's surface towards the Moon, and the gravitational effect is closest on the side of the Earth, which is greatest on the side of the Earth which is closest to the Moon. So there we have a larger, longer, thin black arrow than on the far side. The other force here is that basically the Earth and the Moon are spinning around their axis, and that generates a centripetal force. So those are the thin white arrows, and that centripetal force is outwards. It's away from on the Earth. It's away from the Moon, and that acts in a way that's fairly uniform over the Earth's surface. So here are these thin arrows there, they're away from the Moon. And if you sum up the gravitational force and the centripetal force, we have the overall force that acts on the water on the Earth's surface. That's our tide generating force. And on one side of the Earth closest to the moon, gravity wins out over centripetal force, so we have the water sort of being pulled on this side towards the moon and to give us this bulge. On the far side of the Earth, the centripetal force is greater than gravitational force, so again we have an overall force that pushes water away from the moon, and that creates this second sort of bulge. So that's the basic setup. We think now about one location on the Earth. The Earth rotates on its axis every 24 hours. So if we start on this location on the Earth, after a quarter of a rotation, this part of the Earth will pass through one of these tidal bulges. We then go through a half rotation, and the same position on the Earth's surface passes through the second tidal bulge, then another quarter rotation and we're back to where we started. So basically it's a combination of the Earth's rotation and also the this gravitational and centripetal force acting together, which basically give us the high variation in water depth due to tides. The Spring-Neap cycles, so those are the periods over 2 weeks. Those are basically caused by the alignment of the Earth and the Moon with the Sun. So that creates another sort of force balance, including gravity and centripetal forces, that generates these 2-week cycles. Okay, so that's the theory. Of course, the Earth is not a perfect sphere. We don't have a uniform thickness of water over the surface of the Earth. That was an idealized concept. In reality, what happens is we have continents that break up the water on the Earth's surface. There are locations with deep oceans or locations of shallow seas. And what that does is it breaks up the circulation of water on the Earth's surface. And what I'm showing here is a map that shows it's the circulation of water due to tides in the North Sea. So here we have the UK, here we have the Netherlands, Germany, Denmark. Here we also have Denmark. So let's start off with these black points. These are locations around which we have a circular motion of the tides over a tidal cycle. So you see those black circles have thin black lines radiating out. Those record the position of the tidal wave. This is, if you like, is high tide. As that high tide position rotates over a 12-hour cycle around this point in here. So we go from 01 to 02 to 03 to 04 hours to 05 to 06 to 07 to 08 hours, and we have a complete rotation over 12 hours. Direction of that rotation is indicated by these black arrows. Okay. Now, as the water rotates around that point, that's referred to as an amphidromic point. The name's not too critical. The water basically interacts with the bathymetry and the coastline. So, as you know, in deep water, as the water rotates around that point, the wave rotates around that point. Well, deep water means that there's nothing to really stop that wave as it rotates around. Once we have coastlines and shallow water, well, that acts to basically, we have to push the water onshore into shallow water, or maybe push it into embayments, for example, in here, as the tidal wave rotates around, and then the water has to exit those embayments or areas of shallow water. So essentially, where we have irregularities in the coastline, either because there's an embayment, sort of a funnel shape in the coastline, or because we're moving into shallow water, the sea surface has to rise up as we put that water onshore, and it rises down as the water moves offshore. And that's what gives rise to this height difference between low tide and high tide. And these dotted and dashed lines, pardon me, around here, those are basically indicating the tidal range, the height between high and low tide. And you can see that height difference is most pronounced where we have these irregularities in the coastline. Okay. So here we have a 4-meter tidal range in the Wash and the Humber River. We have, 3-meter tidal range in some of these, the Rhine estuary, for example. So, this helps to explain why we see those height variations, and also, why we have velocity, or the water moving onshore and offshore with a certain velocity. Okay, so the place on Earth where that effect is most pronounced is the Bay of Fundy in Canada. And you can see in here that's a big funnel shape. So the tidal wave has to enter here and exit again as part of this circular motion around one of these points. And you can see here this graph shows basically as we go from the entrance to the of this bay, as we move kind of up through here, basically that distance, we go from sort of minus 100 kilometers here, we go into the bay, up into here. And as we pass up in here, the bay gets narrower, it gets shallower. So basically we're forcing that water through a smaller cross-sectional area, and that means the height between low and high tide, the water level has to go up really dramatically, a large distance. And we see that at the mouth where the bay is wide and deep, the tidal range is just 4 meters. And as we pass up this way into here, the tidal range increases as the bay gets narrower and shallower. Once we get right up into here, that effect is dissipated by friction. The tidal wave gets dissipated by friction in very shallow water. But here the tidal range can exceed 12 meters. Let me show you a picture of that. So here is part of the Bay of Fundy at high tide, fully underwater. Here at low tide, fully exposed. And here the tidal range is about 12 meters. So really quite pronounced. Okay, so what are the characteristics of tides? How do we recognize them within deposits? So here we've got a graph showing time in the vertical axis, and that time is one tidal cycle. So let's say 12 hours in this case. And the horizontal axis is velocity. So this line here is 0, no velocity. Towards the left, that's the flood tide. So that's an increasing velocity moving water onshore. If you move to the right of the 0 line, the velocity increases and the water is moving offshore. It's moving in a seaward direction. So if we start here, for example, this is low tide. Oh, sorry, let's start here. This is high tide, 0 flow velocity, high tide. Okay. The water then starts to fall. We move into the ebb tide, and as the water is falling, the falling tide, when it's falling fastest, we have the highest velocity, and those velocities can be sufficiently high to move sand, generate ripples and dunes, and to migrate those ripples and dunes in an offshore direction. So we can generate a crossbed or cross stratification with a Paley current in an offshore direction. The tide continues to fall, and as it carries on falling, it falls at a lower rate, and at low tide we have 0 flow velocity. So at low tide, 0 flow velocity in the water, mud, silt, fine material can settle from suspension, and we get deposition of mud. Okay, now the tide starts to rise, and as the tide rises, at the maximum rate of rise, that's the highest velocity. Again, we can generate sufficiently high velocities to move sand, ripples, dunes that give us payday currents, cross beds, indicating an onshore direction. We then, the tide continues to rise, but it slows down, and at high tide, again, we have zero flow velocity, mud settling from suspension. So this is the basic pattern. We have this regular interbedding of mud and sand, recording these variations in the strength of the velocity, and we have two current directions which are opposed to each other. One is offshore, one is onshore. Those two things are the characteristic features of tides. Okay, this image is also idealized. We're assuming that those two tides have the same velocity, the same strength, and that's often not the case. So here we're looking at a similar graph. We've rotated it around. We take this graph, we rotate it around through 90 degrees. We don't worry about whether the velocity, whether the current is onshore or offshore. We just say the strength, the speed of the current, and that's our vertical axis. Time now is the horizontal axis. So this is, again, is over a 12-hour period. So in this case, let's say this peak in here, this tide is the ebb tide. That's the falling tide moving water offshore. That's slightly stronger, so it's dominant in this particular example, and therefore the velocity, the speed, reaches a higher maximum. That's what we're seeing in here. We then have zero flow velocity. That's our mud deposition. Then we have the flood tide, the onshore directed tide in this example. The peak is not quite as high, so we say that's a subordinate tidal current, and then down to zero again. Now, to move sand, we have to basically, the current speed has to be above a certain threshold. That's this threshold here in the this upper dashed line. That's a sand transport threshold. So basically, for the dominant tide, this is the time above which the velocity is high enough to move sand, and the amount of sand that we move is basically proportional to the cube of that excess velocity. So in other words, a small increase in velocity gives us the capacity to move a much, much larger volume of sand. The subordinate tide, well, that excess velocity above the threshold is quite small, and therefore we only move a small volume of sand. So what this means is there's a big asymmetry in the size of the crossbeds that are produced by the dominant tide versus the size of the crossbeds produced by the subordinate tide. Okay, let me give you an example of that. So here the dominant tide, high velocity at its peak, we can move a large volume of sand, so we're moving dunes or mega ripples and also ripples. We then have our first period of zero flow velocity. That's sometimes referred to as slack water. That gives us a mud drape. The current then reverses, a subordinate current, but remember this is not as strong, so we don't move as much sand. We erode some of the mud, and we just move a few ripples in this case. We then go to our second period of zero flow velocity, which gives us our second mud drape. So here, this cartoon at the bottom, we're seeing interbedding of sand and mud. We're seeing two current directions, a dominant one to the right, the subordinate one to the left. So we meet our tidal criteria, but we have to look hard to find evidence of those two current directions. It's not as obvious. The same thing happens when we go to longer tidal cycles. So for the Spring-Neap cycles that represent 14 days, for example, here we're seeing speed against time. The time here is 2 weeks, and we're just showing these peaks in velocity. And what you see is, the times when we had the spring tides, those are the big tidal ranges. We can move an awful lot of sand there, and therefore we have, if we're looking at a crossbed that's produced, we have thick sand facets within the crossbed, just thin drapes in between them, thin mud drapes in between them. If we look at then at the neap part of a tidal cycle, these are when we have the lower tidal ranges and the lower velocities. We see the mud drapes are more continuous. The sand facets in between them are narrower. And what that means overall, if we look at the crossbed, we have wide spacing of mud drapes representing the spring tidal period and close spacing of mud drapes during the neap tides. Okay, those are nice line drawings. What does this look like in nature? So here are some examples of crossbeds where you see a regular alternation of sand, mud, sand, mud, sand, mud. That's regular and repeating, so that's good evidence of tides. We don't see the opposite tidal current in this particular example at the top here. The bottom example, something similar, one crossbed, the dominant current towards the right, but you can see in here the sand represented by the pale grey, mud in the dark grey, and we can see there are places where the mud drapes are closely spaced, places where they're widely spaced. So this would be neap tide, spring tide, neap tide. So, we can see evidence in nature of these tidal cycles. Okay, so key tidal processes, regular repeating fluctuations in velocity. This gives us this intimate interbedding of sand and mud, and that can occur across several scales depending on the tidal cycles that we're observing. We see evidence of two opposed current directions, onshore and offshore directed. Sometimes that can be very obvious, and probably the classic textbook example is herringbone cross stratification. One crossbed this way, the overlying crossbed the other way. That's pretty unusual. Normally we have to hunt around and cover a larger area to get and probably usually in 3 dimensions to get a feel for those two opposed current directions. We can also see some more indirect evidence of tides. So often we have mixing of fresh water and marine water, and which gives us kind of brackish water salinities in many tidal environments, and that salinity can change. The expression of that changing salinity can be cracks. Clays, for example, they can shrink and then swell to open up cracks as the water chemistry changes. The clay minerals are charged. They interact with the chemistry of the water, and they open up these thin, rather delicate cracks, which we call syneresis cracks. We can also see this evidence of changing salinity or brackish salinity in the form of animals. So in ancient rocks, we're thinking here about body fossils, and also trace fossils, burrows. And we typically see a low diversity. So reduced diversity indicates basically not many animals, not many types of animal behavior within a particular environment. And that's typical where we have changes in salinity. Okay, so let me show you a model of a tidal flat to begin with. So we've talked about tidal processes. Now let's switch gears to a tidal flat. So this is a 3D block diagram to a tidal flat. The bit closest to us, the front face of the model, is in relatively deep water. The back of the model is kind of closer to land. So we can see that parts of this block diagram are what's referred to here as subtidal. That means they're underwater even at low tide. And often they're characterized by channels or networks of channels. And those channels have dunes migrating through them. We can see evidence of two opposed current directions in those channels, and those represent the deepest water. So sandy cross-bedded sandstone within channels as the deepest water part of a tidal flat. As we move from back up the tidal flat, basically we see we're into this intertidal area. This is covered by water at high tide and it's exposed at low tide. And if we look at the lower part of that tidal flat, this is the part which is underwater for longest. It's dominated by sand, so sandy ripples. There's more time for the tidal currents to move sand around in that part of the tidal flat because it's underwater for longer. And as we move up the tidal flat, the amount of time the tidal flat is underwater decreases, and therefore we tend to have less sand and more mud. So once we get into these shallower water environments, we're looking really at predominantly mud. We also have a network of creeks. So these are channels that drain the water off the tidal flat when the tide falls. You can imagine as the tide rises, the rising water level floods this broad, floods the whole tidal flat. But once the water level starts to drop, any subtle changes in topography on that tidal flat become exaggerated over multiple tidal cycles, and we cut these channel networks which allow the water to drain off the tidal flat. So these are tidal creeks. They're not connected to rivers. They're purely they're purely created by tidal processes. Those tidal creeks migrate laterally, so they have lateral accretion, deposition on one side, and they're typically pretty steep-sided. So here's our intertidal flat, and we can see as we go from relatively deep to relatively shallow, we have an upward decrease in the sand content. And then once we get to the top here, so this is a supratidal area, it's above high tide, this is a salt marsh. So it's muddy and it's characterized by plants that can tolerate salty water. And in this vertical section, you can see roots through there. Okay. So this is an idealized vertical section going from deep to shallow. You'll notice there the deepest part is sandy, the shallowest part is muddy. So there's a difference. This is giving us an upward fining succession as we get shallower upwards. That's the opposite to what we expect in where waves or river mouth processes occur in a shore face or a delta. So this figure here shows that in the context of a sequence stratigraphy and parasequences. So here, this is our cross-bedded sand. This is the deepest part of our tidal flat succession. And as we pass upwards, we go into the intertidal area, which is getting muddier upwards. And in green, we have these rooted mudstones. In this case, they're showing some coal above those roots. So this is an upward shallowing succession, even though it's getting muddier upwards. So this would be one parasequence. Then flooding in this case is marked by a change back into sandstone. The sandstone here represents the deepest part of our tidal flat. And again, as we pass upwards, we get progressively less sand. So fining upwards, recording a change from relatively deep to relatively shallow. So this is the expression of parasequences and flooding surfaces in a tidal flat. Let me show you some examples from a modern tidal flat. So I'm going to show you an example of the sandy part of the intertidal zone. This is taken at low tide, and you can see in this case lots of ripples with the steep faces directed towards the left in this case. Here we're moving up into the upper muddy part of the tidal flat, and we can see the little islands of vegetated material here. That's the salt marsh that's occurring above the high tide level. Again, the upper muddy intertidal flat, and then the salt marsh to the left there. I mentioned we have these creeks, these rather narrow, steep-sided channels cut into the intertidal flat, and in some cases into the salt marsh as well. Here's one example of a creek, or one of these creeks draining into another creek. There's a big accumulation of oysters here, just one species, all oysters piling up these shell banks. So that's an example where the brackish water conditions give us just a very low diversity of animals. Again, here's the edge of one of these tidal creeks, a relatively steep, muddy bank. Once we get into the salt marsh itself, here you can see a pond or a salt pan in the salt marsh, and you can see hopefully there's cracks on the floor of that pond. Those cracks are produced by changes in the salinity of the water. We change from fully marine to partly fresh water. That causes the clays within the sediment here to shrink. As we then add more marine water, those clays expand and they open up these cracks. And here, I think this is the last of these images from a modern tidal flat environment. Here we're looking at, near the mouth of one of these creek networks. This is taken at low tide, and we can see dunes and ripples. We're almost here into one of these subtidal channels. Okay, so just to summarize here, tide-dominated shorelines that, I've talked to a tidal flat. These occur along shorelines with a large tidal range between low tide and high tide. And as we go from the base of the succession towards the top, we get shallower, we have a decrease in sand content. So the deepest part of the succession, we have cross-bedded sandstones and tidal channels. As we pass upwards into shallower water, we gradually lose the sand content in these intertidal flat regions, and then towards the top of the tidal flat succession, we see evidence for exposure, roots, or in some cases, if we're dealing with a very arid climate, we might have evaporite minerals precipitated rather than forming roots and coals. And all of these environments, they're associated with a low diversity of trace fossils and body fossils because there are brackish and changing salinities.